Imagine the night sky erupting with a brilliance that rivals the moon. This isn't science fiction, it's a supernova. These awe-inspiring events mark the explosive death of massive stars. Supernovae are among the most powerful and luminous phenomena in the cosmos. They release tremendous amounts of energy. This energy blasts out across the universe. We've observed supernovae throughout history. Ancient astronomers were stunned by these sudden bright appearances in the sky. Today we use sophisticated telescopes. We can study these events in detail. We can unravel the secrets they hold about the life and death of stars. Supernovae are not just destructive events. They are also essential for cosmic evolution. They scatter heavy elements into space. These elements are the building blocks for new stars, planets, and even life. Without supernovae, our own existence would be impossible. Join me as we journey to explore these celestial wonders. We'll delve into the heart of a dying star. We'll witness the incredible forces that drive these cosmic explosions. We'll discover the profound impact supernovae have on the universe we call home. Stars are born in vast clouds of gas and dust. We call these clouds nebulae. These cosmic nurseries are filled with hydrogen and helium. These are the lightest elements in the universe. They are the raw materials for star formation. Deep within a nebula, gravity draws gas and dust together. Clumps of matter begin to collapse under their own weight. As these clumps shrink, they spin faster and faster. The material at the center heats up. This hot, dense core is called a protostar. Over millions of years, the protostar continues to grow. It pulls in more gas and dust from its surroundings. The temperature and pressure at the core increase dramatically. Eventually, the core becomes so hot and dense that nuclear fusion ignites. Fusion is the process of combining lighter atoms into heavier ones. In the core of a young star, hydrogen atoms fuse to form helium. This nuclear reaction releases an incredible amount of energy. This energy creates outward pressure that balances the inward pull of gravity. A star is born. Once a star achieves nuclear fusion, it enters a long, stable period. We call this the main sequence. Our own sun is a main sequence star. It's about halfway through its lifespan. During this stage, the star's outward pressure from fusion balances its own gravity. The vast majority of a star's life is spent in this state of equilibrium. It steadily fuses hydrogen into helium in its core. This process releases a constant stream of energy. We see this energy as the star's light and heat. The length of a star's main sequence lifetime depends on its mass. Massive stars are much hotter and brighter than our sun. They burn through their hydrogen fuel much faster. Smaller stars, on the other hand, can live for billions or even trillions of years. As a star continues to fuse hydrogen, helium builds up in its core. This inert helium core doesn't produce energy through fusion. It gradually contracts under its own gravity. This contraction heats up the core even further. The ticking clock, fusion of heavier elements. As the core of a massive star contracts, its temperature and pressure continue to soar. Eventually, the core becomes hot enough to fuse helium into heavier elements. This process releases even more energy than hydrogen fusion. Helium fusion produces carbon and oxygen. These elements accumulate in the core, forming a new inner layer. As the star ages, it goes through a series of fusion stages. Each stage fuses heavier and heavier elements. Carbon fuses into neon, oxygen into silicon, and finally silicon into iron. Each stage of fusion releases less energy than the previous one. This means each stage also happens much faster. The star is now living on borrowed time. The grand finale: core collapse and explosion. Iron is the most stable element in the universe. Fusing iron actually requires energy rather than releasing it. So when the core of a massive star is filled with iron, fusion grinds to a halt. Without the outward pressure from fusion, the core can no longer support the weight of the star's outer layers. The core collapses in on itself at an incredible speed. This collapse happens in a fraction of a second. The core is crushed to extreme densities and temperatures. The protons and electrons in the core are forced together. This forms neutrons. This neutron-rich core is incredibly dense. It resists further collapse. The infalling outer layers of the star slam into this unyielding core. This generates a shock wave that travels outward at tremendous speed. The shock wave blasts the star's outer layers into space. This is the supernova explosion. The energy released in a supernova is mind-boggling. For a brief time, a single supernova can outshine an entire galaxy. Stellar remnants, neutron stars, and black holes. The core of the star, compressed to incredible densities during the supernova, is left behind. The fate of this stellar remnant depends on its mass. If the core's mass is less than about 3 times the mass of our Sun, it becomes a neutron star. Neutron stars are incredibly dense objects. They pack the mass of the Sun into a sphere only a few miles across. A teaspoon of neutron star material would weigh billions of tons on Earth. If the core's mass is greater than 3 solar masses, not even the resistance of neutrons can halt its collapse. The core continues to collapse indefinitely, forming a black hole. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. These stellar remnants are fascinating objects in their own right. They offer unique laboratories for studying the fundamental laws of physics under extreme conditions. Cosmic recycling, the legacy of supernovae. Supernovae are not just destructive events that mark the end of a star's life, they are also crucial for the evolution of the universe. They play a vital role in cosmic recycling. During the explosion, the intense energy of a supernova forges heavy elements. These elements are heavier than iron. This process is called nucleosynthesis. These elements are scattered into space by the shock wave. These heavy elements enrich the interstellar medium. This is the gas and dust that exists between stars. This enrichment is essential for the formation of new stars and planetary systems. The heavy elements from supernovae are the building blocks of planets. They form the raw materials for life itself. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in the hearts of dying stars. Supernovae, therefore, are not just endings but also beginnings. They are essential links in the chain of cosmic evolution. They connect the death of old stars with the birth of new ones. They demonstrate the interconnectedness of the cosmos and our place within it.